approach, which is so here, like I kind of skipped with you, but basically we did an explicit, I didn't really do it because I didn't really evaluate these diagrams in front of you, but in principle what we did was an explicit evaluation of the effective Lagrangian, but it would exactly be equivalent to what is phrased as the decoupling theorem of Appel-Princeton, which is kind of the canonical way to phrase EFT. From 1975, which is about the time that all these renormalization concepts were born. So the decoupling theorem tells us that in general, the procedure of integrating out by that, in our case, or whatever high momentum degree of freedom we want to remove from the problem, generates all possible interactions of the fields allowed by symmetries, and the derivatives, allowed by symmetries. So, due thanks to the decoupling theorem, this theorem that was proved and actually exactly shows that if one goes through the explicit process, he would get all possible additional interaction. So the starting point would be actually that. Instead of doing the explicit integrating out, one can just start with the knowledge of this result, just constructing from scratch what is the effective Lagrangian. And this gives rise to the second approach that I was mentioning yesterday, the bottom-up approach. Which means just constructing an effective from scratch by using degrees of freedom and coupling them according to allowed symmetries. So that was the simple example to get you to understand what is the idea. Did the idea pass through? Anyone? Everything is okay? Okay, so that's the simplest example we can get a feel for. And now this will be again a bit of a repetition of what I was talking about yesterday. Today's lecture is dedicated to constructing the tower of the EFTs. And as I explained yesterday, we are going through two stages, which will have, one of them will be using exactly the bottom-up approach. In the first stage, we will be using the bottom-up approach. Obviously, this is formally harder because this is a formal construction. Here, one should go through really thinking about what are the symmetries that are relevant in the effective theory, and what are the degrees of freedom, and how the construction is made. We're starting with nothing. So this is obviously the more formal part of the work. And I will mostly dedicate today's lecture to that, to the first stage. Whereas in the second stage, in our case, we do the top-down approach where we actually evaluate the diagrams. And although this is definitely not trivial, this is rather technical, in the sense that one should not really reinvent the wheel or really think hard what is the physics that is going on. It's more or less straightforward evaluation of final diagrams, of course tackling different things that maybe one doesn't normally see in the context of QFD, but rather technical. So today's lecture will be dedicated more to presenting the first stage, which is the formal construction of the first EFT, the one particle EFT, and tomorrow I will focus on really getting you into the feel of the computations that are done in the second stage to construct the two particle EFT. Okay, but I will now just remind you I think that I was very slow, at least at the beginning yesterday, so it really just be a reminder of what I explained yesterday. Okay, so now we're talking about the tower of EFTs. The tower of EFTs corresponds to the tower of scales. So, for the three scales, we should go in general through three stages. To integrate each of the scales. So, we have this ladder of scales, S, R, lambda. Then, we want to first construct an EFT that will be kind of valid about this in about this range of scale. So here we will construct one particle EFT. At the next stage, we would like to construct an EFT that will apply in about this range of scales. This is the two particle EFT. And finally, an EFT of radiation which will apply far above the radiation wavelength scale up to infinity, to the absorber infinity. This will be the EFT of radiation. In this EFT, we will no longer have any field nodes left. In the case of the conservative sector, as I tried to highlight yesterday, there are by definition no radiation nodes, and therefore only going through these two stages will get us to some sector of the EFT of radiation, and that will be the focus of what I will present in the lectures. So again, stage one, construct one particle EFT. So we remove the scalar S. I'm being quick because it's a reminder, right? Like you remember things from yesterday, right? Yeah. Okay. So I remove the scalar S from the Einstein-Hilbert action. So I start with the action is G is 1 over 16 by G X R. Okay, I make this abstract decomposition of the metric to be those that represent the high momentum, the short scale nodes, and what is beyond the short scale nodes, which is orbital separation scale and beyond, which will be known by G bar. interactions between them. Interactions between them and the remaining degrees of freedom of the field. So among world line and field degrees of freedom. Okay. So just to remind you the expression, it would be S effective, which will be a function of G bar, and the new degrees of freedom, G bar is a function of the coordinates, but the world line degrees of freedom are a function of the defined parameter, the world line parameter, which here I denote by y to distinguish it from coordinates in the field. So my S effective depends now on G bar and the new world line degrees of freedom. If one does not consider spin, the position of the object is enough, but when one considers spin, the electron should be added. So in general, the expression would be the old expression for the Lagrangian now applied to the remaining degrees of freedom of the field. And an addition of an infinite set of world line operators, which would be preceded by Wilson coefficients. The Wilson coefficients will depend on the short scale that is integrated out. And world line operators that will have no knowledge or memory of the scale that was integrated out, and therefore all the scale dependence that will appear here in the operators will be that which contains only higher scales, larger scales. So we have infinite set of operators on the world line. This is what we call the particle part of the action. Where all the Euclid physics goes into the Wilson coefficients. So our task, which we will tackle today for boldly, would be to identify correctly the relevant degrees of freedom and the symmetries that hold the scale, and to couple the degrees of freedom by all possible ways that are allowed by the symmetries. That was a reminder for stage 1. I will give a reminder for stage 2, and then we will get into the details, back into the details of stage 1. Yes.
What is Li actually look like?
What is?
The operators.
Yeah. It would be composed, we will see how it would be composed of the degrees of freedom that you have in your now in your problem. So it would be something that includes the field in some way and the world line degrees of freedom in some way. But when we include the field, it will be the field evaluated on the world. This is important to stress. But this is localized, not global. We will see that. That's the lecture is basically focusing on this statement, but still I want to